Good day, everybody. We're trying to find all non-negative n. The first non-negative n is n equals 0. And what type of n are we looking for? We're looking for n such that 7 to the n plus 15 to the n plus 19 to the n plus 87 raised to the n power is a square integer. Now already you can see 19 is large enough, but 87 would make it unwieldy to do any kind of manual calculation. 19 would for large enough n, right? At 15, all of these grow very fast, exponential growth, right? So let's check out the first few cases that we can calculate. Now, if n is equal to 0, notice that we would get 1 plus 1 plus 1 plus 1 equals 4, okay? So our expression here, let's call it e. Let's call it e just so I don't have to write it down. Our expression e for n equals 0 is 4. Which is a perfect square. 4 is equal to 2 squared, right? Okay, so that's simple enough. So we have 1. It says find all n a member of z, the non-negative integer such that the expression is a perfect square. We have 1. Let's check out n equals 1. The last one that's an easy calculation. Okay, this would imply that e is equal to 7 plus 15. Anything raised to the first power is the anything, right? Plus 19 plus 87. All right, now let's add this up and see if it is a perfect square. I'm getting 22 and 19 is 41. 41 and 87 is 128. Now 128 does not equal a perfect square. 64 would, right? But 128 is not equal to a perfect square. I'll call it k squared if you want. Okay. So far we only have 1, and the calculations for n equals 2 would be too much for us right here already, right? So we need to come up with another approach here to determine if there are any other n. So far this is the only one that checks the box. All right, so let's move along. Now, a super important result here that cuts down on the amount of calculations we have to do is this result right here that says k squared. Let me get my marker back up. Where'd it go? K squared. This result right here, the lemma, it says, whoops, there I am. Okay, it's the only way I can find it. Okay, k squared is congruent to 0, 1, mod 3. Now, you only have to check mod 3. Every integer has a remainder of 0, 1, or 2, right? Any integer you can think of when you divide it by 3 only has 3 possible remainders, namely 0, 1, and 2. So it's clear that 0 and 1 are possibilities, right? But the only other thing you really have to check is 2 squared. But 2 squared is congruent to 1. Mod 3. And again, it's enough to check. You'll learn that in number theory if you just take an elementary number theory course. You can see, most of you probably already know all this stuff, but modular arithmetic is sometimes called remainder arithmetic. Okay, so for all k a member of z, k squared is either 0 or 1 modulo 3. So you see we can check our expression here with regard to this lemma. 7 is congruent to 1 mod 3. Notice I left out the modulus here. It's mod 3. 7 is congruent to 1 mod 3 because 7 minus 1 is 6, which is a multiple of 3. 15 is congruent to 0 because 15 minus 0 is a multiple of 3. 19 is congruent to 1 because 19 is equal to 6 times 3 plus 1. And 87 is a multiple of 3 also. And notice, y'all, we are, with regard to doing this all mod 3, I don't have to keep writing it down. Now, a nice thing about this is that one benefit of working this is that you can treat this congruence just like equality. You can raise both sides to the n power, and you get 7n is congruent to 1. 15n is congruent to 0. 19 raised to the n is congruent to 1. Raising 1 to a natural number power is just gives you 1 back, right? 19 to the n is congruent to 1. And 87 to the n power 87 raised to the n power is congruent to 0. And this is for all n, okay? So we have two instances. 7 to the n is always congruent to 1. 19 to the n is always congruent to 1. The rest of them are always 0, right? So if you go down here, you can see where we got this. You have 1, 1, 1, 0, 1, 0. Okay, now this is equal to 2. Okay, and so this is mod 3, of course. So our expression is 2 modulo 3. The expression we're interested in being a perfect square is 2 mod 3, right? It's 2 mod 3, but notice anything that is a square has to be congruent to 0 or 1. We're, yeah, right here, folks, okay? Any squared object is going to be 0 or 1 mod 3. That's for all k. Yet right down here we got the expression of interest is congruent to 2, right? So that means that what that is telling us is this is not a square integer, this expression that we're interested in. For we've already done cases 1 and 2, right? So for n greater than or equal to 2. And we already know that really should just be 1 there, I guess, you know. But this result right here really proves just this for now, because we've already shown up here what happened in the n equals 0 case. N equals 0 case, we got our only perfect square. And then n equals 1 case, we didn't get a perfect square. Okay? So that does it, folks. That says that's it. I mean, find all n. This is the only one. N equals 0 is the only one that meets the description. And I do want to say that this is only this wouldn't work as well, you know, if we didn't get something like this. If we didn't get 2, we wouldn't really know anything. We just happen to know that since we got 2, it can't be a square integer. But going the other direction, you wouldn't know too much about this. You know, if you couldn't get this to resolve to 2, you wouldn't be certain whether or not. Just because something is congruent to 1 doesn't mean it's going to be a square mod 3. Okay, but a square is congruent to 1 mod 3. You know, it's not bidirectional. Okay, but anyway, that's it, folks. We didn't have to do any manual computations. Modular arithmetic saved the day for us on this particular problem.